Hello again. You know, it's almost time for me to go now. I've been materialised a little bit too long and I need to fade away and recover a bit of energy. So, before I do go, however, what I want to do is to give you one last thing to think about. I want to talk about innovation and how innovation can drive change. Sometimes that change will be the difference between a business surviving and a business collapsing. I'm going to do this in terms of a real-world example, one that happened within the last 20 years, the lessons from which are transferable to all the challenges coming up in the future. We're going to look at a branch of chemistry derived from synthesis gas. We're going to look at acetyls, specifically acetic acid. We're going to see that in this particular case, innovation surrounding how acetic acid is manufactured saved an industry. We'll also see that the decisions to either go ahead or to abandon a technology are incredibly multifactorial. They stem way beyond just technological ability to a very complex picture involving the business world, the safety world, the supply chain world. Let's start by having a look at how acetic acid is made. So here on the whiteboard is the equation, chemical equation used to make methanol. So synthesis gas, carbon monoxide and hydrogen, is traditionally used to make methanol, and that methanol is further combined with carbon monoxide to make acetic acid. This is not the only route through which acetic acid can be made, but it is by now far the most popular route. Once you have acetic acid, you can add ethylene to it to make ethyl acetate. Ethyl acetate is a very, very commonly used solvent for inks. Pretty much every inkjet printer will have ethyl acetate as its ink solvent, and is also a very important pharmaceutical building block. We can add ethylene and oxygen to acetic acid to make something called vinyl acetate monomer. As the name suggests, monomer, we can polymerise vinyl acetate monomer into polyvinyl acetate. PVA, as it's sometimes better known, you'll find in glue. No doubt, probably in primary school, you used PVA wood glue. It's polyvinyl acetate. It's found in paints, it's found in paper coatings. So the message I want to get across on this slide, that once you have synthesis gas, you have the ability to make methanol, the ability to make acetic acid, and the ability to make a lot of quite important intermediates that will end up as consumer-facing products. The solvents, the pharmaceutical building blocks, the paper coatings, and so on and so forth. Now, this process was itself new in the late 1970s. This was how to make acetic acid from methanol. Previous production routes didn't involve methanol, but the Monsanto process was a pioneering step. What the Monsanto process does is bring together carbon monoxide and methanol in the liquid phase for methanol, so the carbon monoxide is bubbled through that methanol, in a slurry of catalyst in a stirred tank reactor. The products from this stirred tank reactor are separated and the catalyst is recovered. Any methanol that is lost during this product recovery is recycled. It's cleaned and recycled back into the reactor loop. Now, the catalyst that is used makes quite a few byproducts, so there's several stages of separation needed to make pure acetic acid. The first thing to do is to get rid of the water and separate that out. The second thing is to separate out key chemical impurities, specifically propionic acid. And the third thing to do is to then purify the acetic acid to the required purity for further processing. So we have the core of the plant, the reactor, producing a product that requires 4 stages of separation. So, the catalyst that does this is quite expensive. It's hydrogen iodide in the presence of a rhodium complex. So, this catalyst produces a significant amount of byproducts, which results in this large separations process. So we have the reactor, the core of the plant, and then all the distillation systems trying to get rid of the stuff that we actually don't want, but has been produced anyway. One of the key byproduct reactions that this catalyst has is something called carbon monoxide shift. Whenever you have carbon monoxide in the presence of water, you're going to get an oxidation to carbon dioxide and production of hydrogen. And sometimes that can be a very, very useful reaction. Sometimes it can be highly undesirable, and in this context, it's highly undesirable. Now, Suppose we want to innovate. Suppose we want to make this process cheaper. We've got a lot of energy wrapped up in separations here. We could increase our product specificity with a better catalyst. And so a novel catalyst developed by BP called Cativa not only was more selective, but it was cheaper. This was a hydrogen iodide catalyst in the presence of iridium and ruthenium. Moreover, it had better selectivity. Less byproduct was produced, only 2 distillation columns were needed. The really nice thing is that the environmental performance was better. Carbon monoxide shift was suppressed, 30% less carbon dioxide waste was produced as a result. The nicest thing of all was that the Cativa catalyst could be effectively retrofit into existing acetic acid plants. Let's see how they did it. So, the novel catalyst was put into a reactor system that was effectively the same reactor system that it was for the Monsanto process. So you've still got methanol in the liquid phase, you've still got carbon monoxide bubbling through that methanol, and you've still got a suspended catalyst within that liquid methanol. However, after that, things are changed. There's fewer byproducts, so catalyst recovery is easier. It simply needs a vapor-liquid separation. After that, you've only got to deal with effectively 3 problems: water, propionic acid and acetic acid. So the first step is drying, and the second step is purification. So 2 distillation columns rather than 4, fewer reboilers, less energy overhead, a far more efficient process energetically. So, what were the development considerations? First of all, safety. Safety of the process and safety of the materials used. If we think of the process, what conditions does the reactor operate at? Are they the same as the existing catalyst, or are they more benign? Are the pressures lower? Are the temperatures lower? What about the material safety? The material being the catalyst and the chemistry used within the reactor? Well, again, you've got to look at your catalyst and assess its toxicity. Is this a catalyst that is going to be harmful? If it is there something more inherently safer? In terms of what your catalyst is reacting, in this case we have methanol and carbon monoxide. Carbon monoxide is pretty hazardous. We're not introducing anything increasingly hazardous, so in effect we're maintaining the status quo by maintaining the same raw materials. Other things we've got to think about: process operability. Does the catalyst actually work sufficiently well enough for an industrial process to be built around it? It might well work very well in the laboratory, but what happens when you've got 1.5 tons of catalyst in a great big reactor? How quickly does it deactivate? Can we reactivate it? Are there side reactions happening at scale due to mass transfer limitations that we haven't seen in the laboratory? Is the catalyst handleable? Can we actually maintain these reactors? Can we replace catalyst in a meaningful way when we have to? Or even better, can we regenerate it in situ? What real-world process benefit does this new catalyst actually bring us? Okay, in the laboratory we've seen an improvement. Does this actually factor out as a real improvement at plant level though? If it's only a few % difference, does this actually motivate us to want to go ahead? If it's 50 to 60% difference, then that's strong motivation to go ahead. And so the real-world process benefit has to go hand in hand with the economic benefit. Really, what we're seeing an incremental shift that in real terms makes very little difference, or are we seeing a paradigm change in how we make this chemical product? There's lots of other things to think about as well. What's a development timescale, for example? Typically, it can take up to 10 years for a new plant technology to make its way from the laboratory to a chemical site. The fact in this case that you could retrofit cut that timeline in half. It was about a 5-year development timeline before the catalyst was installed in the first plant as a retrofit. Don't forget, during that time, your competitors may well be gaining competitive edge. What's your catalyst supply chain like? If you're dealing with a new catalyst, who's going to make it? Are you going to make it? Are you going to get a subcontractor to make it? How many subcontractors are going to be making it? Are you going to be satisfied that having one production company alone gives you sufficient integrity to your supply chain? What happens if they become bankrupt? You've lost your only manufacturer. What happens if they suddenly decide to increase their price because they hold a monopoly position? Your process economics could be badly, badly affected. How are you protecting these developments? If you've truly found something inventive, how are you protecting that intellectual property? How are you preventing your competitors from effectively copying what you're doing? Are you going to keep things trade secret? Are you going to patent protect? Part of patent protection, however, is publishing what you've done. Do you want that information in the public domain or not? Don't forget, a patent is only worth as much as you can afford to defend it with. So if you can't afford to defend your patent in court, even if someone does come along and steal your technology, what are you going to do about it? So, what I wanted to do in this part of this lecture was talk a little bit around innovation. Innovation sometimes is the key to survival. In an increasingly cost-competitive world, it's sometimes the new innovative processes that will have the leading edge for years to come. I wanted to paint a picture that shows innovation also as being commercially risky and lengthy, because both these facets of innovation are true. We saw, in terms of a real example, a catalyst change making a big difference to the financial overheads of running a plant, an improvement in this case. This was through quick deployment and the ability to retrofit this technology. If this technology had required a new plant to be built, the business case may well have been very, very different, and I probably wouldn't be talking about it right now. So we've talked about a success story, but don't always assume that innovation brings success. It depends on a multifactorial problem. It depends on how that success is influenced by your supply chain, by intellectual property, by business factors, by economic factors, by safety factors. So, innovation is important, but always go into innovation with your eyes wide open.